Good morning, dear students. Am I audible?
Good morning, sir.
Parso, am I audible?
So, yes,
Okay,
sir.
okay. Uh, yes. So I think all of you have watched yesterday's video. So how to memorize the thing, okay? Because it is uh, everybody's actually it is habit that after few days, whatever you just study or whatever you try to commit to your memory, you just forget after 15-20 days, isn't it? So gradually, so it actually vanishes from our memory. So I think the last video I shared, it will help you in committing to memory, okay, whatever you just study, because it is very much necessary for you to remember all the formula, all the concepts, okay. So let's come to our main agenda. So we were actually discussing uh, the logarithmic decrement in the damped vibration, isn't it? So the logarithmic decrement, which is denoted by delta, so for two consecutive, okay, for two consecutive amplitude on the same side of the mean line, so it was given by delta equals to log base e, so xa divided by xb, and its value or its magnitude is given by 2 pi zeta divided by under root 1 minus zeta square, isn't it? So if the zeta value is small, so we can neglect this term, okay, so it will be only 1, so this term will become 1, so delta will be equals to 2 pi zeta, okay. So zeta value where it is having some decimal, okay, very 0.004 or 0.003, then we can neglect this value of this denominator, okay. So delta will be equals to 2 pi zeta, so that is what it is written, okay. So if you are given the initial amplitude, okay, and the end amplitude, okay, maybe it is amplitude after 3 cycle, after 5 cycle, after 6 cycle, means the last amplitude, okay, n number of amplitude after n number of cycles, let's the vibration it vanishes, okay. So you know the initial amplitude, you can measure, okay, the initial amplitude on the same side of the mean line, and you will be able to measure the end amplitude, okay, after n cycle. So if you just uh, this one by n, if you take 1 upon n, means this is n is the number of cycles. Suppose after 5 cycles your amplitudes are given, so it will be 5. If it is 6 cycle, then it will be 6. So 1 upon 6 log base e, so x naught divided by x6, so then you will also get the value of this logarithmic decrement, okay. So delta, so it is basically constant, okay. So this value is constant, so this is x naught, and let's say this is x3, so 1 upon 3 log base e x naught by x3 will give you the logarithmic decrement value. And for 2 cycles if you consider, so 1 upon 2 x naught logarithmic log base e x naught by x2 will give you the logarithmic decrement value delta, that is constant, okay. And this one you can prove by this derivation, okay, very small derivation. Just you need to take the ratio of this consecutive amplitude x naught by x1, x1 by x2, so its value you know, because x naught by xn you know this value e to the power delta and e to the power delta, isn't it? So here e to the power delta, this ratio e to the power delta, from here you can write xm will be equals to e to the power delta, that is what you have written, okay. And finally after multiplication and taking the logarithmic value, so you will get delta will be equals to 1 upon n log base e x naught by xn, okay. So this is for n cycle, okay, and this is for one cycle. You can say this is for one cycle. Okay, so initial value and the final amplitude on the same side of the mean line. Understood? So I have given this problem, numerical problem, to you. I don't know how many of you just tried to solve this problem. So again, I will be taking the same problem. So here the question goes like this: the disk of a torsional pendulum has a moment of inertia of 600 kg centimeter square. Just wait. So 600 kg centimeter square and is immersed in a viscous fluid. Okay, so this is viscous damping. So in a container, so there is a viscous fluid. Let's say some oil it is there. Okay, so some oil it is there, and in that oil, so one disc which is having moment of inertia, so it is just round. Okay, so its moment of inertia is 600 kg centimeter square. Understood? So the brass shaft attached to it is of 10 centimeter diameter. So the shaft by which the disc is connected, so it is of brass material and it is having a diameter 10 centimeter. Okay, it is a stiff rod, so its diameter is 10 centimeter. Okay, and it is 40 centimeter long. Okay, so it is just like a torsional pendulum. So it is immersed in the oil. Okay, so which is having some viscosity. Okay, so yeah, when the pendulum is vibrating, so how it can vibrate? So it can rotate. Okay, so if you just give some initial displacement, what will happen? It will rotate. Okay, inside the oil. Okay, and it will create the vibration, isn't it? So the observer amplitudes on the same side of the rest position, mean position, for the successive cycles are 9 degree, 6 degree and 4 degree. So why it is greater 9 degree? Because initially it will vibrate in a longer angular deflection, isn't it? So 9 degree. Then due to the viscosity resistance, so this there will be a decrease, okay, in the amplitude. So it will be 6 degree and then it will be 4 degree. So basically it is just like an experiment. Okay, so the same type of experiment it is there in your lab, and we will show you how this angular displacement, okay, or angular deflection, it happens, okay, on this disc. Okay, so what is basically given? So one disc, metallic disc, it is immersed inside a container which is having some liquid, and it is joined by a stiff rod, because to rotate on its axis, so one stiff rod should be there which is having a diameter of 10 centimeter. Okay, and the disc is having a moment of inertia of 600 kg centimeter square. Understood? And when the disc rotates, okay, means it will be twisting and untwisting. It will be creating a motion of twisting and untwisting. So it is deflected initially to an angle of 9 degree. Okay, then next angular deflection is, or displacement is, angular displacement is 6 degree, and after third cycle, so its angular displacement is 4 degree. So gradually it will decrease, because in the logarithmic decrement, in the damped oscillation, what we have studied, that it will decrease, the amplitude will goes on decreasing after every cycle. Okay, that is why there will be a resistance, there will be damping in the system. Okay, so what you are asked to find out, so determine the logarithmic decrement, then damping torque at unit velocity. Okay, so first we are going to find out this logarithmic decrement. Just wait. So how we can find out? So we are having this angular displacement on the same side of this mean line, because for the successive amplitudes, angular amplitudes on the same side, it is given on the same side. Okay, so it is 9 degree, 6 degree, 4 degree. So if you just take the ratio 9 degree by 6, means 9 by 6 or 6 by 4, and if you take the logarithmic natural log base e, okay, so then you will get the value of this logarithmic decrement. So delta is basically what? Log base e 9 by 6. As because there are two amplitudes, so we will be just taking the normal formula, okay, the initial formula for two successive amplitudes. This one, delta will be equals to log base c xa by xb 2 pi zeta under root 1 minus zeta square. Understood? So delta will be how much? So log base c 9 by 6. You can take 6 by 4 also like this, or log base c 6 by 4, because you are considering this consecutive amplitudes. You cannot take 9 by 4, okay, because there will be two cycles, okay, to go from 9 to 4, okay. So only you need to take this consecutive value. So log base is 6 by 4, so its value will be 0.405. Understood? So this is delta. Again, this delta is how much? So this magnitude of this delta will be equals to 2 pi zeta under root 1 minus zeta square. You have got this formula from here, okay. So delta will be equals to 2 pi zeta under root 1 minus zeta square. Okay, so from here, so you will be able to find out the value of zeta, okay, this damping factor. So if you just square both the sides, first we will be taking this denominator to left hand side, so 1 minus zeta square, and then squaring, what you will get, so this will be removed, under root sign will be removed, and this will be delta square. Here it will be 4 pi square zeta square, and after simplification, what you will get, the zeta value will be equals to delta by under root 4 pi square plus delta square. Okay, very simple calculation. So if you just put the value of delta, so you will get the value of zeta. Okay, so why you are doing all these things? Because you are asked to find out the damping damping torque per unit velocity. Okay, damping torque per unit velocity, actually this is nothing but the value of damping coefficient. Okay, so this is nothing but this damping coefficient. So you are asked to find out this value of this value c, okay, damping coefficient. Another value is cc, critical damping coefficient. So damping torque at unit velocity is nothing but the damping torque. Okay, so why I am saying it like this? So if I will ask you that what is the value of damping force, so it is cx dot, isn't it? So if you are asked that what is the damping force at unit velocity for linear vibration, so it is damping coefficient. Okay, because for linear velocity, so we will calculate damping force, and for this is angular vibration, isn't it? This is torsional vibration, that is why it is damping torque. Okay, so damping torque per unit velocity. So what will be its value? So t, if t is the torque, then its value will be c into x dot. Are you getting what I am saying? C into omega dot or x dot. Okay, so damping torque at unit velocity. So if velocity is unity, then damping torque will be equals to what? C, isn't it? So that is why you are asked to find out the value of damping coefficient here. Okay, so to find out the value of C, so what was the formula? So the formula to find out C is this one, zeta. Yes, C is what? Zeta 2 under root kt into I. So how this will come? So I will tell you. So first, what you need, just try to remember that the damping coefficient value is 2 zeta under root kt I. Okay, so I will tell you how this formula will become this one. Okay, so to find out C, so you need to find out zeta, you need to find out kt, and you need to find out this I. Okay, means a moment of inertia, you can say. Okay, so here it is written as J or whatever it is, but it is moment of inertia. Okay, so you can write I and you can write J, but you need to define it. Okay, otherwise there will be a clash between the polar moment of inertia and the normal this one moment of inertia. Okay, so here, though it is written as J, so it is basically moment of inertia. Understood? So we need to find out the value of zeta, and we need to find out the value of kt. So to find out the value of zeta, so we are actually using this formula. Okay, so delta you have found out, then from this formula you will be getting this value of zeta. Okay, now how you can find out the value of C or CC? So C by CC is what? Zeta, isn't it? So C is what? So zeta into CC. Okay, and what is CC? So Cc, how we have defined? So Cc by 2m equals to how much? Under root k by m. This is omega m, isn't it? So in the analysis of the over damping system, okay, or in the damped vibration, so we have taken Cc by 2m equals to under root k by m, which is equals to natural frequency of the system. So Cc will be how much? So km under root k by m. So this will be multiplied to this term into 2m. So 2m, if you just take 2m under this radical sign, then you need to write 4m square, isn't it? So if you just take out, then you will get 2m. So k by m into 4m square. So mm will be cancelled out. So 4km. Understood? So 4km. So if you just take out 4, then it will be 2 under root km. So this equation or this expression is for linear vibration. Understood? So 2 under root km is the value of critical damping coefficient for linear vibration or translational vibration. But our vibration is what type of vibration? This is torsional vibration. So k will be replaced by kt and m will be replaced by I. So 2 under root kt into I. Are you getting what I am saying? So from here, these values, Cc value can be written by 2 under root kt by I, kt into I. Okay, so here k into m under root k into m, but this is angular displacement, okay, angular vibration. That is why 2 under root kt into I, and the value of c will be how much? So zeta into 2 under root kt upon kt into I. Understood? So now what is your task? Now you need to find out the value of kt, okay, and you need to find out the value of I value is given. It is 600 kg centimeter square. So if you just convert it to kg into meter square, so you need to divide it, okay. So 0.06 kg meter square. Understood? Because centimeter 10 to the power minus 2 into 2, so 10 to the power minus 4, so 0.06 kg meter square. Understood? And B is given, L is given. So now you will be able to find out the value of torsional stiffness for the stiff rod. Okay, so one stiff rod which is made up of brass, it is attached to the disc. So the value of kt already we have found out in the free vibration. So kt will be how much? So zj by l. So z means polar moment of inertia, or you can write ip. Okay, ip means polar moment of inertia. So kt value will be z by l. Z is the Young's modulus. Okay, so z by l, so pi by 32. So for cylindrical stiff rod, the polar moment of inertia is given by pi by 32 d to the power 4. Understood? So it is the value is given as 4.4 into 10 to the power 10. Z value is given in the question. Then 0.4, if you convert it to SI unit, so 0.4 meter. So if you just put it, so you will get the value of kt as 1.08 10 to the power 6 Newton meter per radian. Okay, because this is torsional stiffness. Okay, so you have got all the values. Zeta value you have found out, kt value you have got. Okay, so you now you can find out the value of c, because I value is also given or z value is also given. So if you just put it, you will get the value of c as 32.8 Newton meter per radian. Its unit is very much important. Okay, so the damping coefficient unit is Newton meter per radian, or the critical damping coefficient unit is Newton meter per radian, but the unit of zeta is, it is unitless, because this is the ratio between c and cc. Understood? So this way you need to solve. Okay, so step by step you need to see the problem. Okay, and whatever the things you are asked to find out, so first you need to write that thing. Okay, because this is logarithmic decrement, so logarithmic decrement directly you can find out from the consecutive amplitudes, or from this direct formula. Okay, if you know the value of zeta. But here you are asked to find out the value of zeta. Okay, because you need to find out the damping torque per unit velocity. Okay, so for any damped means Coulomb damping, okay, or viscous damping, what actually we have seen at the very beginning when I told you about the various types of damping system, that this damping force, okay, it is very much dependent on the relative velocity. Okay, so basically F equals to what? C x dot, isn't it? So this is for linear vibration, and for angular vibration, so if it is tau, torque, okay, torque is tau, then it will be what? So c into omega. Okay, c into omega means angular velocity. Understood? So see, if omega is unit velocity if you take, then damping torque will be equals to tau will be equals to C into 1. Okay, so it means you need to find out the damping torque per unit velocity, that is damping coefficient. Understood? So this problem is not that tough, but these formulas, okay, so how you will be able to memorize this formula. So from here only you need to apply, okay, this concept. C by Cc will be zeta. So Cc is what? Cc by 2m will be equals to under root k by m. Okay, so which is equals to omega n. So from here, so you will get that C will be zeta into 2 into under root kt into I or j. Okay, so I is the or j is the polar moment of inertia of the disc. Okay, and here torsional stiffness, you need to take the diameter of the stiff rod and length of the rod which is attached to the rotor. Understood? Yes, any doubt? Tritiraj? Nilo?
No, sir.
Understood? Tritiraj?
Sir.
Have you got the idea how you will be solving this problem?
Sir,
Or little doubt?
গোটেই পোৱা নাই
Okay,
চাব
so
লাগিব sir
yeah, actually
ভালদৰে
the thing is that this is actually 2-3 classes previously 2-3 classes I have actually shared this PDF file. Just you go through it, okay, after this class, and I will upload this video in the Google Classroom. So if you just find out any problem, you just see the video, and after that also if you don't understand, then you can ask me, okay, personally, anyone, okay, anyone of you can ask. Okay, so this is all about the natural this one logarithmic decrement. Okay, yeah. Next, we'll be starting this one, dry friction or Coulomb damping. So I have already given this file to you, and I have actually consider this as a classwork, okay, for you, okay, self-study material, but I don't know how many of you have gone through it. Anyone who has gone through it? Rajdeep, have you seen the pages? Avinash?
Present, sir.
Yeah, I have asked you something actually. Have you gone through the PDF file for this dry friction or Coulomb damping?
Not yet, sir.
Yeah, why? Rajdeep?
I will go through it.
Okay, okay. Actually this is not that tough thing, okay, just the mechanics thing, whatever till now you know the friction force. So it is what? F equals to mu r. So where there will be friction without lubrication, so how the friction value will behave with respect to velocity. Okay, so this is all about that concept only. Okay, so this is basically the theory and the analysis part. So here it is given. Actually I have taken this from a very good book. Okay, it's this book is by Grover. Okay, Mechanical Vibration by Grover, ZK Grover. Okay, so very conceptual book. So you can also have that book, okay, to understand the concepts. So basically what happens, just an overview I will give you, but in the next class so I will clarify this concept. So what happens, see, so let's suppose this is a surface where the mass, okay, where the mass it is sliding, because in machineries what happens, most of the parts they are unlubricated. Okay, in shaper machine, when the surface, okay, the tool surface, it is just touching the workpiece surface. Okay, so basically there is no lubrication. If more heat is there, then we use some coolant, that is a different thing. Okay, so here no viscous oil it is used. Okay, so what will happen, this mass when you will displace to the right side, so one motion, okay, so what will happen, so it will be completing at the very beginning, it will be completing the quarter cycle to the right hand side, then again it will come back another quarter cycle, means half cycle will be completed, then again it will go to the left side of this mean line, because this is the mean line, isn't it? So this third quarter cycle, and again it will reach the original position. Okay, but it will cross definitely because there is not much damping. Okay, so it will try to cover, okay, some cycles. After that only it will be stopped, isn't it? So after 4 quarter cycles, so it will complete one cycle. So first, when you will displace this body to the right hand side, so 1 quarter cycle, then when you are displacing the body towards right, then movement is towards left, that is another quarter cycle, and the left hand side, okay, so another third quarter cycle, and the another right hand side, fourth quarter cycle, then this body will be completing one complete cycle. Are you getting what I am saying? So this is one cycle, then consecutively this will happen, okay, and at each of the cycle the amplitude of the body will goes on decreasing, isn't it? Because there is resistance, there is friction. So depending on the smoothness of the surface, okay, so it will be also dependent on time also. So the decay of the amplitude will go on, and finally the motion will vanish and the body will comes to rest. Okay, so this is what is actually basically the dry friction or Coulomb damping. Okay, so basically this is the brief introduction of this Coulomb damping. So we will take this topic in the next class. Okay, so thank you for listening. So if you have any doubt, then you can ask me or you can leave the meeting. Thank you.